Click. The light turns on. You've done this 1,000 times. It feels instant, simple. Just a switch, a wire, and a bulb. That's all there is to it, right? Wrong. What is actually happening inside your walls isn't a simple flow. It is a strange, invisible dance. A chaotic, beautiful catastrophe that connects this tiny bulb to the very structure of the universe. And it is absolutely nothing like what you were taught in school. We all have this picture in our heads. We imagine a wire is like a garden hose. You turn on the tap, the switch, and electricity flows through the empty pipe like water, rushing from the power plant to your lamp. It's a clean, easy idea. But there is a problem. If you take a pair of scissors and snip that wire open, what do you see? Is it hollow? No, it is solid copper. It isn't an empty road waiting for traffic, and it is already full. That wire is absolutely, completely jam-packed with electrons right now, even when the switch is off. They are crammed in there like marbles in a tube, shoulder to shoulder, jiggling against each other with no room to breathe. So, if the tube is already full, how exactly do we manage to shove anything else in there? Let's look closer at that garden hose idea. It's the favorite analogy of every high school physics teacher. You have a tank of water, the battery. You have a pipe, the wire. You open the valve, the switch. And whoosh, the water rushes through the empty pipe to spin a little wheel at the end. It makes perfect sense. It feels right. But nature is trickier than that. Nature doesn't like empty pipes. If you could shrink yourself down, way down, smaller than a dust mite, smaller than a virus, and you stood inside that copper wire, what would you see? Would you see a long, empty tunnel waiting for a spark to come zooming down? No. You would be crushed. You would be standing in the middle of a dense, chaotic, vibrating crowd. That copper wire is a solid block of matter. It is made of copper atoms, packed tight in a crystal lattice. And swarming around those atoms are the electrons. They are already there. They've been there since the copper was mined from the ground. They were there when you bought the wire at the hardware store. They are part of the copper itself. Think of a long tube, clear plastic, extending all the way from one side of the room to the other. Now, imagine we fill that tube with marbles. Not just a few. We pack them in, tight, one touching the next, all the way across, no gaps, no air, just marbles. That is your wire. It is chock full. This changes everything we think about turning on the power. When you flip that switch, you aren't pouring new electrons into an empty wire. You can't. There is no room. It is a solid deadlock. If you try to shove an electron in one end, where does it go? The tube is full. And it's a traffic jam where the cars are bumper to bumper, stretching for miles. So, here's the puzzle. If the wire is already packed solid, and the electrons are squeezed in tight against their neighbors with nowhere to go, how on earth does the light turn on the instant you flip the switch? How do you move something that is essentially stuck? Here is where it gets really strange. We all know electricity is fast. You flip the switch and, snap, the light is on. It feels instantaneous. It feels like the speed of light. So, naturally, we assume those little electrons inside the wire must be zooming from the switch to the bulb at millions of miles per hour, like little race cars on a perfectly smooth highway. But they aren't. They are shockingly, impossibly slow. If you could paint one single electron red, just to keep track of it, and you watched it travel down that copper wire while the light is on, you would get bored very quickly. It isn't racing. It is crawling. It is barely moving. In fact, a garden snail, a literal, slimy snail, could overtake that electron without even trying. In a typical household wire, the actual physical speed of the electrons is often just a few millimeters per second. It's lazy. It's sluggish. It takes its sweet time. If the power plant is a few miles away, The electrons that are in the generator right now won't reach your house for years. Why? Because it's not a highway in there. It's an obstacle course. Remember, the wire is solid. The electron tries to move forward, but bam, it hits a copper atom. It bounces back, jiggles sideways, tries to go forward again, smash, hits another one. It's a random, chaotic walk. It is wandering around, aimlessly jiggling, and only very, very slowly drifting in the general direction of the light bulb. And this creates a massive problem, a paradox that should bother you. If the electron leaving your light switch takes an hour to actually reach the lamp on the ceiling, well, why does the light turn on the moment you touch the switch? You don't flip the switch and then wait an hour for the fuel to arrive. It happens instantly. The cause and the effect seem to happen at the exact same time, yet the things carrying the energy are moving slower than a bug. So, how is that possible? How does the energy get there at the speed of light if the carriers are stuck in traffic? The answer lies in understanding the difference between the runner and the race. To see it, we have to leave the world of atoms for a moment and go to a football stadium. Imagine the stands are packed, thousands of people, shoulder to shoulder, and suddenly, someone starts the wave. You know how it works. You stand up, throw your hands in the air, yell, and sit back down. Then your neighbor does the same, then their neighbor. Now, ask yourself, did any single person run across the stadium? No, you stayed in your seat. You moved maybe 2 feet, up and down. But the wave? The wave traveled all the way around the arena in seconds. This is the secret. Electricity is not the flow of the people. It is the flow of the wave. Inside that copper wire, the electrons are like those fans in the stadium. And they are packed in so tight that they are practically touching. When you flip the switch, you aren't waiting for an electron to run all the way to the light bulb. You're simply shoving the first electron in line. And because they are jammed together, that first electron has no choice. It bumps into its neighbor. Snap. It gives it a little push. And that neighbor immediately pushes the next one. And the next one. It is a chain reaction. A domino effect of tiny, microscopic shoves. The individual electron barely moves. It just wiggles in place. But that pulse, that energy of the shove, travels through the crowd of atoms at nearly the speed of light. It is a shock wave. So, while the electron itself is moving slower than a snail, the signal is screaming down the wire. That is why the light turns on instantly. Yet you aren't sending fuel to the fire. You are sending a command through a long line of soldiers, and the message travels instantly, even if the soldiers stand still. But to really understand what is happening, we have to throw away the marbles. We have to stop thinking about dominoes falling over. Because if you look deep enough, electricity isn't mechanical. It is something much more ghostly. There is a silent, invisible actor in this story that we haven't talked about yet. It is the puppet master, the electric field. This is the part that usually gets buried in math equations, but it is actually quite simple and incredibly strange. When you connect that battery or flip that switch, you aren't just pushing the first electron in line. You are establishing a field. Think of the electric field like a command from a general to an army. Imagine you have 1 billion soldiers, the electrons, standing in a long line. If the general wants them to move, he doesn't walk up to the first soldier and shove him. No. And he shouts a command. Forward march! That command travels through the air. It is invisible. It has no weight, but it carries authority. When you flip the light switch, you are the general. You send a signal screaming down the wire at the speed of light. This isn't a physical object. It is a change in the state of space itself. It zips through the copper, ignoring the atoms, ignoring the traffic. And the moment that field arrives, every single electron in the wire, whether it's right next to the switch or 50 feet away in the ceiling, feels a force. They all feel a tug. It's like a magical wind that suddenly blows through the entire wire at once. The electrons at the far end, near the light bulb, don't have to wait for the ones at the switch to bump into them. They don't have to wait for the push to travel down the line. The field is already there. It surrounds them. It grabs them. It tells them, move, and they obey. Billions of them, all at once, start to drift. They start to jiggle and flow. This is the beauty of it. The energy, the thing that actually lights up your room, isn't carried inside the little electron bodies. It isn't in the particles at all. The energy is carried by the field. It is carried by the space between the electrons. The electrons are just the workers. They are the gears that grind and heat up the filament to make light. But the thing driving them, the thing delivering the power, is this invisible vibrating structure that extends through the universe. So, where does this field come from? What creates this invisible command that tells the universe to move? That brings us to the source, the battery. And I promise you, and a battery is not what you think it is either. We tend to think of a battery like a bucket full of electricity juice. You plug it in, you pour the electricity out into your phone, and when the bucket is empty, the battery is dead. It's a nice image. It makes sense. But it is completely wrong. A battery is not a storage tank. A battery is a pump. To understand what it's actually doing, we have to go back to that idea of work. Think of a large, heavy rock sitting at the bottom of a hill. It is happy there. It is stable. It has no energy to give you. If you want that rock to do something, if you want it to smash something or spin a wheel, you have to do work first. You have to pick it up, carry it against gravity, and set it on the very peak of the hill. That is exactly what a battery does to electrons. Inside that little metal cylinder, there is a chemical war going on, and the chemicals are doing heavy lifting. They are taking electrons from the positive side, where they are happy and comfortable, and forcibly dragging them over to the negative side. They are piling them up, squeezing them together against their will. The battery builds a hill, and those electrons, they hate it there. They are packed tight, repelling each other, vibrating with tension. They are desperate to get back down. They want to return to the positive side where there is room and balance. But they can't. The inside of the battery is blocked. The only way down the hill is through the wire. So, when you connect a wire, you are building a slide for the rock. The electrons see that open path and whoosh. They tumble down the wire, crashing through your light bulb, spinning your fan, doing work on their way back to the bottom. And this is why we call voltage electric pressure. It is literally the measure of how high the hill is. It is a measure of how desperate those electrons are to escape the crowd and get home. When a battery dies, it doesn't mean it is empty. The electrons are still there. The copper and zinc are still there. It just means the chemical workers inside are too tired to lift any more rocks. The hill has flattened out. The pressure is gone. So, the battery doesn't make electricity. It creates the tension that makes electricity move. It turns a peaceful piece of metal into a loaded spring, waiting to snap. Now, there is one more twist. One more deception that is happening right now in the walls of your house. We've been talking about electrons moving down a wire like a slow river or a falling rock. That is true for a battery. That is direct current, DC. But the electricity that powers your lights, your fridge, your computer, that comes from a plug in the wall. That is alternating current, AC. And here is the mind-blowing part. The electrons powering your computer right now have never left your house. In fact, they have probably never even left the copper wire inside your wall. They certainly didn't come from the power plant down the road. If you could zoom in on one of those electrons, you would see something almost comical. It isn't flowing anywhere. It is just wiggling. It moves forward a tiny fraction of an inch, then stops, and then moves backward, forward, backward, 60 times every single second. It is trapped in a tiny, microscopic box, just jiggling back and forth for its entire existence. So, if the electrons aren't going anywhere, how does energy move? How does the power plant send anything to you if the delivery trucks, the electrons, never leave the garage? Think of a saw, a big two-man lumberjack saw. You push it, you pull it, push, pull. The saw blade itself doesn't go anywhere. It stays between the two men. But the energy? The energy travels through the blade to cut the wood. Or think of sound. When I speak to you, the air molecules in my throat don't fly across the room and hit your ear. They just vibrate back and forth right here. But that vibration bumps the next molecule, which bumps the next, and the sound travels. And that is what AC electricity is. The generator at the power plant isn't pumping water. It is grabbing the electrons at one end of the citywide wire and shaking them. Push, pull, push, pull. That shake travels through the miles of wire all the way to your house and shakes the electrons in your wall. And that jiggling motion, that frantic, desperate dance, is what heats up your toaster filament or spins your fan motor. The electrons themselves? They are just dancing in place, right where they have always been. But there is a price to pay for all this jiggling. There is a cost to this dance. We often notice that when we use a lot of electricity, like with a hairdryer, a toaster, or even just the charger for your laptop, the cord gets warm. Sometimes it gets dangerously hot. Why? If electricity is just a field telling electrons to move, why does it generate heat? To understand this, we have to look at the road conditions inside the wire. We tend to imagine the electron acts like a car driving down a clear, open highway. But remember, the wire is made of copper atoms. Big, heavy, stubborn copper atoms. And they are everywhere. For an electron, moving through a wire is not like driving on a highway. It is like trying to run through a crowded market, blindfolded, at full speed. The electric field shouts, "Move!" and the electron rushes forward, and it accelerates. It gains energy. But before it can get anywhere, smash! It slams headfirst into a copper atom. It stops dead. It bounces off. It gets disoriented. But the field is still there, shouting, "Move!" So it picks itself up and starts running again. Crash! It hits another atom. Run, smash. Run, crash, run, bang. This is happening billions of times every second for every single electron. It is a scene of absolute violent chaos. And here is the key. Energy never disappears. When the electron slams into that big copper atom, the energy of the crash has to go somewhere. It goes into the atom. The electron hits the atom so hard that it makes the atom shake. It gives the atom a kick. Now, imagine billions of electrons crashing into billions of atoms, all at the same time. The entire structure of the copper wire starts to vibrate, and the atoms start buzzing and shaking violently in their seats. And in physics, that vibration, that jiggling of atoms, is exactly what heat is. Heat isn't a fluid. Heat is just motion. When you feel your phone charger getting warm, you are feeling the microscopic bruises of 1 trillion tiny car crashes. You are feeling the energy of the electrons being transferred, through violence, into the structure of the wire. We call this resistance. It sounds like a polite electrical term, but really, it is friction. It is the struggle of the electrons fighting their way through a solid object. And sometimes, we want this struggle. Inside your toaster, we put a wire that is intentionally hard to get through. We force the electrons to crash so much and the atoms to shake so violently that the wire glows red hot. At that beautiful orange glow of a heater is literally the visual evidence of a subatomic traffic disaster. So, We have a picture of these clumsy, slow, blindfolded electrons crashing into things, getting bruised, and barely moving forward. It sounds pathetic, doesn't it? It sounds weak. But electricity is not weak. It can melt steel. It can stop a human heart. It can power a city. How can something so slow be so powerful? The secret is not in the speed of the individual. It is in the overwhelming power of the crowd. Imagine you are standing on a beach. If one single drop of water hits you, you don't even notice it. It is harmless. But if 1 billion tons of water hit you all at once, that is a tsunami. The water molecules in a tsunami aren't moving faster than the water molecules in a garden hose. There are just more of them. It is the same with electricity. When you turn on a simple 100-watt light bulb, and you aren't sending a few electrons down the wire, you are commanding an army. In just 1 second, you're moving roughly 6 billion electrons through the filament. That is a 6 followed by 18 zeros. It is a number so big, it becomes meaningless to our brains. To give you an idea, that is more electrons passing through your lamp in 1 second than there are grains of sand on every beach on Earth combined. This is the true definition of amps. People think amps are about how fast the current is flowing. No. Amps are a measure of the crowd size. High amperage means a wider river, a bigger mob, a heavier glacier. And that is why electricity is dangerous. It isn't a bullet, it is a glacier. A glacier moves incredibly slowly. It creeps. But because it has so much mass, so much stuff moving together, and it can carve through mountains, it can crush rock. This is the profound realization about the universe at this level. One electron is insignificant. It creates no heat, no light, no magnetism. It is a ghost. But when you get them to move together, when you get a trillion of them to jiggle in unison, they become a force of nature. They become a collective monster that can heat the air to create lightning or spin the motors that drive our civilization. The power doesn't come from the particle. The power comes from the unity. But there is one final question. We know how they move. We know why they heat up. We know there are billions of them. But where did they get this energy in the first place? If we trace the wire back, past the outlet, past the city lines, all the way to the source, what do we find? If you trace that copper wire back, out of the wall, out of your house, across the city lines, eventually, you end up at the source, the power plant. There, giant magnets are spinning to push the electrons. But what spins the magnets? Usually, it is steam. And what makes the steam? Fire. We burn coal or oil to boil water. But ask the question a child would ask. What is coal? It looks like a black rock, but it isn't. It is the crushed, fossilized remains of a tree that lived 300 million years ago. And what did that tree do for its entire life? It stood there, bathing in the sun. It performed a miracle. It took carbon dioxide from the air, just floating gas, and it used the energy of the sunlight to force those atoms to snap together into solid wood. It was storing energy. It was a battery being charged by a star. Every ounce of energy in that piece of coal is just captured sunlight from a summer day before the dinosaurs walked the earth. For millions of years, that energy slept underground. It waited in the dark. Until we dug it up, put it in a furnace and burned it. And what is burning? Burning is just running the movie in backward. We break those carbon bonds, and the energy that was trapped inside snaps back out. So, look at the light bulb in your room right now. Really look at it. That light is not electricity. That light is the sun. It is the exact same sunlight that fell on a prehistoric jungle an eon ago. It was caught by a leaf, stored in a trunk, buried in the earth, dug up by machines, turned into heat, then into steam, then into magnetic motion, and finally, into the jiggling of electrons in your wall. It has taken a strange journey through time and form, but it is the same energy. When you flip that switch, you are not just completing a circuit. You are opening a time capsule. You are releasing a ghost of the ancient sun to shine in your living room tonight. It turns out that electricity isn't just a utility. It is the way the universe remembers the light. So the next time you walk past that little plastic switch on your wall, pause for a second. Don't just look at it as a tool. Don't just see it as a way to make the dark go away. Look at it for what it really is. It is a trigger. When you flip that switch, you're not just completing a circuit. You're orchestrating a symphony of impossible things. You're waking up the ancient ghosts of the sun, trapped in the earth for millions of years. You're commanding a field that stretches across the entire universe. You're forcing trillions upon trillions of lazy, blindfolded particles to dance, to crash, to scream, and to shine. And you're doing all of this with the tip of your finger. We think we understand the world around us because we have named it. We call it electricity. We call it voltage. We act like because we have a label for it. And the magic is gone. But the more we look, the more the magic deepens. Because I have told you how the electrons move. I have told you how they push each other and how they jiggle. But I haven't told you why. Why does one electron push another away? Why is there this invisible force, this charge, that refuses to let them touch? Why is the universe built on this tension, this desperate need for space? If they didn't push each other, matter would collapse. The chair you are sitting on would dissolve. You would fall through the floor. The only reason you can touch anything, the only reason you exist at all, is because of that electric repulsion. But why is it there? Why does the universe behave this way? That is the deepest question of all. And the answer to that, well, that is a different story entirely. I'll leave you to imagine it.